Yes, thank you very much. Welcome to the Monarch Initiative seminar series this time. Today, my name is Adam, and I'm presenting our paper, an ontology-based rare disease common data model, harmonizing international registries, FHIR, and phenopackets. Ah, okay, yes, I have no conflict of interest, and I'm funded via Professor Sylvia Thun in Berlin, from the Berlin Institute of Health. So I'm also working, Professor Oya Bayan in Cologne. This is where I studied medicine for the most part. I'm now in my final year, and she's supervising also my doctoral thesis. I'm also working for Sylvia Thun at the core unit for digital medicine and interoperability in Berlin, and also with Peter Robinson and the Monarch Initiative. So when it comes to rare diseases, just I'll give a brief background about our topic. When it comes to rare diseases, there's over thousands of different rare diseases, with estimated of 30 million people in Europe and 300 worldwide, potentially even more. Even though there's no cures yet, there's still a substantial amount of population affected by rare diseases. And if you, as the name tells, the patients and the individuals are like scattered all over the world. So therefore, in order to make studies and to generate knowledge about these diseases, we need the data with whom on which we base our knowledge on. We need it to be fair, findable, accessible, interpretable, and reusable. So what is interoperability? There's four layers, main layers: technical, syntactic, semantic, and organizational. The ones we are mainly affecting right now is syntactic and semantic interoperability. So it's, in generally speaking, the unambiguous definition of clinical data elements. So semantic, in this case, means that it's like a shared and precise interpretation of medical data. With this, we use like ontologies and terminologies such as SNOMED, CT, LOINC, Mondo, or the HPO. Now we can perhaps a very short thing to say about ontologies. Why are they so important, and what is this precise interpretation of medical data? You know, as everyone's discussing about artificial intelligence in medicine, there's a nice metaphor we can think of. Imagine we try to basically artificial intelligence trying to look for patterns between data to make some assumptions. And when we translate this, for example, to a chessboard, we could generate or we could develop an AI that when a player does a very good move, perhaps the eyebrow moves, and therefore we can deduct like an AI, we could deduct that when the eyebrows moves like this, then the player will do a very good move. Perhaps we can also do it with a hand movement. So when the player does a good hand movement, they will have a good move. However, this is all still not to the very ground level of medical reasoning and medical knowledge, because it's often with abstract data, it's often with unstructured data. And so ontologies aim to go all the way down to the chessboard layer to really go try to define an objective, to try to objectify the reality, like the phenotypes and the diseases and so on, so that we are all the way to the chessboard layer to have high precision. And this is why ontologies can be so important. And how are ontologies built? They're usually built in a tree-like structure with dependencies between each other, so that a dislocated hip is not just a dislocated hip, it's also a dislocation, it's an abnormality of the hip joint, but also abnormality of the hips. Well, now that's nice to have, but how do we, for example, process and capture this data? So even imagine we have these HBO codes for these three symptoms. How do we organize and arrange them? We could separate them with commas and stashes and so on. But what happens if we even add dates to them? When are they, were they observed, and so on? And this is why we need syntactic interoperability. So semantic is very, very important, but it doesn't, it's not entirely enough. And we also need syntactic, which is a communication then via compatible formats and protocols. For this, we mainly need and also use HL7 FHIR and the GA4GH phenopackets standards, which define the specific kind of like a house or like a structure how this data must look like so that it becomes machine readable. So what is FHIR? FHIR stands for Fast Healthcare Interoperability Resources and is made up on a few blocks and which, for example, houses these definitions like a condition block or an observation block. And within FHIR, for rare diseases, mostly important, we need to look at the International Patient Summary and genomics reporting. The International Patient Summary is a summary of the most essential health data formats and health data information which we need if we want to think globally, perhaps, and which is developed under HL7, currently in version 2.0. But of course, we also, as 80% of rare diseases are genetically based, we also need the genomics reporting implementation guide on which our data model is based as well. FHIR is rather in a transaction format, which makes sure that data comes from A to B, and this is what it has been developed for. It also allows analysis. Basically, you can do analysis on anything. Is when we think back on the chessboard again, but it's inherently made for transaction. And then there's the phenopacket schema, which has been released 3 years ago by now, and in the center of it is a phenopacket here in black. So one phenopacket is one individual, and then you can add specific blocks to it, like an individual, a disease, which you can repeat, and a phenotypic feature, and so on. With phenopackets, we have the ability, it's a quite lightweight format, it's more lightweight than FHIR. We have the ability to map and to create cohorts very easily, or more easily than with FHIR. And one example how then, for example, we can create a more specific, more precise phenotype is that we don't only have the infantile spasms, but we also have the severity, the how often it came and the onset. So everything we as doctors would want to know, and we ask anyway in our clinical anamnesis, we can then put into a structured format so that even those things we also consider for a specific phenotype, which are very important very often, we can also put into this standardized format. It's also an ISO standard, the phenopacket schema. So now we come to our data model. So we've developed a rare disease common data model, which is ontology-based. Our methodology included the inclusion of an assessment of other rare disease data models. We map the mapping to FHIR and phenopacket elements. We also evaluated clinically every single element and also the data granularity for this data model. We have encoded with ontologies, encoded every element on all value sets, also with cross-validation. We implemented it prototypically in 4 different university hospitals in Germany with different use cases, sometimes analysis purposes, sometimes registry purposes. And we've also implemented this in Art Deco and GitHub, including its documentation. All of this happened over the last 3 years, actually, by now. So it was all of it kind of like a non-hierarchical process with loads of learning, feedback, and so on. And yeah, very interesting happened. So what is our data model based on? In Europe, we have these European reference networks, which is I'm not sure, but it's over 20 reference networks for specific disease groups and specific specializations. And at the core of this European reference networks, we have the we have the set of common data elements for rare disease registration. It's a set of around 18 elements, so very brief, and it defines what kind of elements are inside and which ones must be captured. However, as you can already see in this small snapshot, they were not defined with ontologies. They were not defined they were not based on FHIR or phenopackets or anything else, but they were just semantically defined. But as we all know, with even in the clinic every day, when I look at the patient records, there's loads of different ways of, even if I have the same elements I'm asking, there's so many different ways of, writing this paper, this information down. And the same happened actually in the European reference networks. That is very great that everyone uses them. They're obliged to use them. However, we see that there's a lot of variation between the reference networks, how they capture the data. One very important example is also in France. I don't Banque Nationale des Données Maladies Rares. Very interesting that in France they have a French system where, based on this data model, over 1 million patients have already been captured with their data model, because the rare disease centers get financed only if they actually capture the rare disease patients with this data model. So based on the cases, they actually get funded. So they are kind of leading in this way. However, this data model was also not entirely based on FHIR, but it's already very, very important step towards harmonization between rare diseases. And there's also other implementations, such as an OMAD we considered, and also disease-specific implementations, but we don't need to go further in these right now. So our definition was that this European data model on the bottom left, we took as a base. We defined this is every single element of this must be inside, so that we can feed the European reference networks, and also, of course, other registries worldwide, because in the end, it's similar data elements that are being asked. So we defined that all extensional elements around the RDCDS, this is the abbreviation for it, must be based on FHIR or Pheno packets. For this, we used FHIR version, the base resources 401, and also the genomics reporting for the genetics. And for Pheno package version 2.0, and the main meta blocks we used was, of course, the individual interpretation, disease measurement, and phenotypic feature, meaning that in the interpretation, for example, of course, we went all the way down to genomic interpretation. And these are the main blocks we we feed with our data model. So all data elements and all value sets were encoded with specified with ontologies or specified codes where possible, preferring snow-city, but also otherwise, for example, for phenotyping, HBO, of course, and others, NCIT, allowing for measurements mainly in genetics as it is defined in the genomics reporting. We encoded and validated it with multiple co-authors, and one rule we defined is that if a value set exists but cannot be mapped to the other standard, like FHIR or Pheno packets, the entire value set is adopted to ensure consistency. This means we'll come to that later, but FHIR doesn't inherently adapt in ontologies always, such as the not constant as well, but encounter, for example. The encounter value set is encounter doesn't play a role in Pheno packets, but in FHIR it's quite important due to the linkage of hospital data. And the value set then has been adapted completely with the FHIR inherent codes instead of also encoding these. Then we also created an article repository, which is like a data modeling tool, an open source data modeling tool with whom you can model and data models, and also link its respective ontologies and terminologies. But mainly, we also defined or developed a GitHub repository, which is creating its own JSONs and CSVs automatically, and validating them against the JSON 2020 schema definitions, so that we have a reliable API we can extend on. We have a specific version now published, and we can then also develop further versions and so on to maintain a robust architecture. We've also developed a Sphinx documentation, which is linked to the GitHub repository with, for example, resources where you can download the Excel table and the JSON files. And also you can see some more information about usage and how to contribute with GitHub issues and so on. This may also be extended in future versions, and we're welcome for feedback on this. So let's go to the actually rare disease common data model. If we take a look at it, this is the entire data model. For those familiar with the RGCDS, I'll show you the sections in a second, but we've adopted also the main sections, so personal information, patient status, and so on are the same as in RGCDS. So here you can see the sections also. In orange, the pseudonym, we called it formal criteria because we added the date of admission. The personal information became date of birth and sex at birth are the same elements, and also vital status and time of death is the patient's vital status and time of death in here. I see a chat. Something if you yeah, there's just the GitHub, yes. And for example, the undiagnosed case, which is actually in section 6, we put to patient status undiagnosed case. Why is this important? Especially for undiagnosed rare disease registries, or we have cohorts where, at some point it's undiagnosed, at some point it's not, and so on. The care pathway, for example, here's a difficulty how the European rare disease common data set was not defined well enough, that it says first contact with specialized center. However, we had to split this, of course, because on the one hand it's a date, on the other hand it's the type of encounter. So in our data model, this element is, for example, then the combination of 4.1 and 4.4 in our data model. By the way, the code RDC is a custom code we defined because in any terminology on ontology, we couldn't find a rare disease specialist center yet. So if anyone finds in SNOMED or somewhere else or in current versions, please let me know. Otherwise, we wanted to make a request at SNOMED to define this code because we think it's definitely an important code to have. So for disease, for example, the age of onset and age of diagnosis from the European core data set is equivalent to our elements 5.3 to 5.6. We have the elements disease and genomic diagnosis. For the diagnosis section, this is important to also be able to link multiple variants to diseases, but also on the other hand, have multiple diseases that may not be the one rare disease. So by splitting it up and linking it, but also linking it or allowing the possibility to link, but also allowing it to be separate, we just enhance the variability of how rare diseases are. We have to keep in mind that there are some rare diseases with multiple variants that may be causing, and so on. And also the HGVS, and so 617 to 6110 is included in the European Common Data Set as 6.2 in the right. So we have different ways of expressing the HGVS and also, of course, the gene as a code from HGNC. Phenotypic findings is, as you can see here in the right, the phenotype code defined as HBO, which is just the code itself. The remaining section here is based on the phenotypic feature section from phenopackets. So basically exactly all of this to be able to make sure that we have very comprehensive phenotyping possible. Then based on our we defined for elements 6 to 5 to 6 to 7, so severity, age of onset, temporal patterns, we defined value sets that are not any value sets, but are also those we have in the phenopacket store, where we processed and captured thousands of phenopackets based on case reports, and we have already had similar or even the same value sets used, for example, for onset. This is important and allows users of the data model to have more harmonized cohorts within themselves, so that you have better comparison available. And the measurements section is also entirely based on the measurements of phenopackets. The family history, for example, is based on the family history core base resource. But with rare disease specific elements, for example, propositors, the relationship propositors and consanguinity, all of this is very important for rare disease analysis and also making a family tree in human genetics. However, you can also express many of this with the family, what's it called in phenopackets? Family. You can create a family as a cohort itself and then link them together. The consent resource is not very important for packets, but for registry especially. So we have the elements agreement, for example, for contact and so on. We have them within 7.4 to 7.7. And the rest to feed the consent resource, we added 7.1 to 7.3. So the status data and health policy monitoring, because they are obliged to be able to create this resource. And of course, the disability code as ICF as the last section of the European core data set. So our data model itself, we have defined, there are schema definitions with the data element code, data type, terminology, or element code system, data specifications, the value sets, the mappings to FHIR and Pheno packets, and a brief description. And all of these are then, for example, they correspond to the X columns. So if you look at the Excel sheet, but they also correspond to the JSON specifications we defined, so that we have a similar way of defining them. We identified three categories for evaluating then our rare disease common data model, which is actually clinically, from the clinical perspective, I found most interesting. That we have a data model, but we wanted to put it in context before, for publishing, and also for us to make sure to know what we actually developed and how we can proceed in the future, and what the difficulties were. And as it was a very large model and a very large topic to address, we've identified these three categories: medical data granularity, medical reasoning, and clinical relevance, and interoperability and harmonization, to evaluate our data model and just not have it stand there, but to really think and to express how in the last 3 years we worked and what kind of insights we had. For the medical data granularity, so granularity, for those that don't know it, means the level of detail within data. So you can either just have the phenotype itself, but you can also have the date, the status, the severity, and so on. So you add more granularity, so you more data and detail to it. So we iterated through all data elements multiple times, actually. But within that paper of this common data model, we assessed the inclusion and exclusion criteria, and we explored clinical relationships between data elements. For specific use cases, you have to be aware of what are the use cases you can feed or you can use with such a data model. And the difficulty lies in the contradictory aims of a data model itself. That you want to, on the one hand, you want to be very comprehensive to allow specialized level research for any rare disease. But you also want to be as compact as possible, of course, to enhance straightforward usability and deployment, knowing that there's also a concept of domain-specific elements that at a certain point, for example, we work together with immunologists, we work together with neurometabolist specialists, and also neuromuscular specialists, that at a specific point, you have to say, all right, this is, clinically, we want to express this in an extension around such a common data model. So this navigating the spectrum of data granularity was the most one of the most difficult parts, actually, which is also not finished, will probably never be finished, which we defined in this current version, but which will still be difficult, still something to address in the future. For this, we also had a requirement analysis, which we published at the Medical Informatics Conference 2024 last year. For medical reasoning and clinical relevance, we try to examine the impact on the medical reasoning process of our data model. So what we identified, that the conversion of clinical data into data elements itself is actually key, but also varies between use cases. So it requires careful review of specific limitations, and also that we found that the semi-automation or automation in some way, in any way, will definitely be, for implementation, will definitely be indispensable. But of course, there's like HGVS validation, which must remain manual. We also try to align our data model with clinical workflow from top to bottom, more or less, of course, to kind of display a patient history and to improve implementation later on. For example, we added unknown values in some cases and so on. And we also found that, of course, that the limited scope simplifies implementation. We don't have therapies so far, which could be an extension at some point. But this said, again, the limited resources in rare diseases must make semi-automation indispensable, which is why we definitely need some ways of semi-automating it, because there's loads of amounts of data and Excel sheets and other ways that is already out there, but which will, based on this implementation, which will not be feasible if everything would have to be captured manually. And in rare diseases, some of you may know the DUC test, which is in rare disease also maybe may lead to a potential bias, which is inherent in this data model. So the DUC test is a principle that if you look at a duck and it says like it sounds like a duck, it looks like a duck, and it moves like a duck or something, that it may be a duck. But if you look underneath the duck and you find batteries, then you may have the wrong abstraction of what you're actually looking for. And in rare diseases, it's similar that you don't look for the needle in the haystack, but you look for the needle in the needle stack because you don't know what you're looking for. And if you don't know what you're looking for, but you already have a specific limited scope of your analysis or of your reasoning capabilities clinically, then you also may run into potential biases, which of course, for now, for rare diseases, we need to increase the amount of analyzable and machine readable data. On the other hand, you always have to keep this in mind that when developing great algorithms or something, that you may run into biases. Something similar we published earlier already with a seminar with medical students in Cologne, and published a perspective also where we consider the medical reasoning on which we also found out about this data model. And in interoperability and harmonization, we analyzed the alignment of data elements with these international data standards. So the difficulty was that we had to find with our approach a common denominator through ontology harmonization of FHIR phenopackets and this registry common data set. Upon development, we identified specific layers for each element, for each concept in a way, layers of harmonization. So the first layer is the alignment layer. So whether the element itself is aligned and mapped to these international data standards. How about the labeling layer? How the data element is labeled, or the concept itself? Which kind of terminology is it bound to? Which kind of code? Which data type does it have? For example, there's this, in FHIR we have a codable concept, but in phenopackets we have an ontology class. So there's it's similar, but it's not exactly the same, which we harmonize as a code itself on ontology code. But as you can see, so it was an indirect, for example, in this case, it was an indirect harmonization. They were harmonized indirectly, but there's still something unharmonized about it, so to say. And the value set layer, so the value set itself, and also the choices of the value set themselves, whether encoded according to these phenopackets of FHIR, whether encoded or whether exchangeable or expressible in these data standards. And we identified a challenge which has been previous, which I mentioned earlier, the term info challenge, that terminologies and ontologies were not inherently put into FHIR. It's rather that FHIR was developed and then they adapted terminologies and ontologies one after another. However, as we found out that also in our case, there were some inaccuracies what FHIR has, which is very precise, but if sometimes these concepts they have were not expressible in ontologies and terminologies, either one of them is either the ontologies also, as inherent as in their nature, they develop further. And of course, there's concepts missing, but FHIR also had an issue with terminologies itself sometimes. But we found out that more than 96% of elements of our data model are aligned with FHIR phenopackets, more than 87% of value sets, value types 85%, and the remaining, you could ask, okay, what about the rest? Well, the remaining, as you saw earlier with the registry data sets, there are some rare disease specific elements that couldn't be encoded yet, or that had some issues with it. So that in future versions we may increase this alignment. On the other hand, you have to always think, okay, there's multiple use cases for each for using this data model, so that this is also feasible. And yes, so this is, for example, the delta. The delta, what are this? The delta, for example, there was also these data elements from the FMDSRD, which is the French data model, or clinical concepts currently uncodable sometimes, which we may need to address in future versions. Well, all of this may seem for the technical people with technical background, this may seem the whole layer of harmonization may seem logical or something that would have been thought about. However, when I learned all of this from a clinical perspective, this was actually then the result of trying to develop this data model. All of this was luckily published recently, and so there you can find all the specifics and all the details about all the evaluation sections. So I would recommend reading the evaluation, which is content-wise probably became the most interesting parts. So what is the outlook? What are we aiming to do in the future? The idea is, of course, okay, all right, we have a nice data model now. Let's streamline like automized implementation into any hospital information system. There's the idea of domain-specific extensions and updates around the common data model, which is basically the European reference networks for these specific clinical domains, such as inborn errors of humanity, with whom we are working together right now. But of course, also others may adapt the similar approach, the methodology, to improve their domain-specific data models as well. We are for version 2.1. We are thinking about, or we're thinking about integrating LinkML more inherently, as when we developed the data model, I just heard or learned more about LinkML, and we found it's like it's a data modeling language, a standardized data modeling language with whom you can use a lot of tools with, and you have an even more standardized approach of expressing your data model itself with loads of functionalities. So instead of having my own JSON schema, you could also have your own JSON schema in LinkML, but you can have loads of other functionalities around them. And we implement other feedback we already received, and we would also think about connecting RareLink, the FIRE IPS, which is International Patient Summary, and genomics reporting more natively. And our data model could also then serve as a potential baseline model for country-specific rare disease common data models. So RareLink, as I said before, what we are currently working on is a novel rare disease framework in REDCap, linking international registries, FIRE and phenopackets, which is also then, if someone had the question, okay, earlier in our methodology, how did we actually do the clinical implementations? We did it via REDCap due to its advantages of simple implementation usage, and we found that it may be very feasible to have this data model entirely implemented for others to use within REDCap. And in the end, last thing to say, of course, our common data model is community-driven, same as everything that should be in rare disease research. We are open to collaborate, exchange, and feedback to enhance this data model to see where it goes. Of course, this is a version now published, but we are happy to improve this in future. So thank you very much for it's in German, sorry about that. Thank you very much for your attention, and I'm looking forward to hear and to discuss.